For an AI to feel truly conversational, the system must process audio and return a response faster than the human brain perceives a delay. This creates a strict mathematical limit, a total loop time from ingestion to response of under 800 milliseconds. This 800 millisecond budget is shared across 6 distinct stages: audio ingestion, voice activity detection, speech-to-text, LLM inference, text-to-speech synthesis, and egress. Synchronous CRUD architecture relies on individual request-response cycles. This overhead consumes a large portion of our latency budget before AI inference even begins. To manage this complexity, developers are increasingly turning to autonomous AI coding agents to architect and build the system. However, without specific constraints, an AI agent will default to generic, monolithic boilerplates that cannot meet these high-performance requirements. Successfully leveraging AI for system design requires translating distributed systems theory into a series of executable, restrictive prompt constraints. This is the role of the system prompt. It acts as a blueprint that forces the AI to align with high-performance architecture through 3 specific pillars: strict isolation, defined performance bounds, and self-documentation. By treating the AI agent as a junior developer requiring mathematically defined guardrails, we can achieve sub-800 millisecond performance. The first constraint we establish in the prompt is strict isolation between the system's core components. This structural separation ensures the AI does not bleed complex business logic into the infrastructure layers. We apply this first to the /gateway ingress orchestrator. Standard HTTP requests create a bottleneck at the gateway. Each connection requires its own handshake, adding delay to every interaction. The prompt directs the AI to eliminate this overhead with a protocol upgrade handshake, transforming individual requests into a persistent bidirectional WebSocket stream. To maintain this stream across distributed nodes, the system requires Layer 7's sticky session routing. This routing ensures that every audio chunk from a specific user is consistently directed to the same processing node. To protect the latency budget, this specific routing logic must execute with absolute minimal overhead. By isolating the gateway in the prompt, the agent is forced to resolve the connection overhead before it ever addresses the data processing logic. The second prompt directive establishes explicit performance bounds, specifically targeting event loop blocking hazards. This is vital for the /STT streamer microservice, which handles the ingestion of chunked binary audio. We utilize bidirectional gRPC streams here to provide high-throughput, low-latency transport for binary data. Our explicitly defined primary risk is dense data serialization. Standard asynchronous code operates on a single thread. When a large binary audio chunk arrives, it monopolizes the thread. This creates an I/O block, causing data to queue up and quickly exceed the 800 millisecond limit. An unprompted AI will typically generate this single-threaded code because it is the most common pattern for standard web services. Our prompt's explicit warnings force the agent to discard simple synchronous serialization. Instead, the AI implements worker pools to offload dense deserialization from the main event loop. Defining these specific I/O hazards up front prevents the AI from creating latency traps that are difficult to identify after the code is generated. Next, we look at the /orchestrator engine, the brain of the system. This engine manages real-time thread allocation for continuous audio streams, operating within a strict ecosystem boundary, the token rate limits of downstream AI models. Managing these limits requires the orchestrator to maintain state, which increases the risk of thread starvation or lock contention. The CAP theorem shows every architectural choice carries a cost. We must choose between high availability, low latency, and absolute data consistency. To meet the 800 millisecond deadline, the orchestrator must prioritize availability, accepting the tax of potential state drift or minor consistency errors. An AI agent will continue to prioritize perfect consistency unless the prompt explicitly instructs it to sacrifice that consistency for the latency budget. The final safeguard in the system prompt is a mandate for the AI to be self-documenting. This is handled by the /architecture component, a dedicated repository for architectural decision records that track every major trade-off. The prompt requires the AI to generate a record before it makes any structural changes to schemas or gateways. This process forces the AI to mathematically validate its proposed implementation against the 800 millisecond boundary. The result is a cohesive, low-latency architecture where every component, from the gateway to the streamer, operates within the required timeframes. Complex back-end engineering is too nuanced for zero-shot AI generation to handle reliably. The role of the senior engineer has shifted toward defining non-functional requirements and identifying I/O bottlenecks, encoding the operational contract that the AI must follow.